physical description of this water hammer, that as a result of closing of this valve, so a pressure wave set up, and this pressure wave travels between the reservoir and this valve back and forth, and because of this we have this pressure variation diagram you can see with respect to time. And we also saw how to calculate this increase in pressure. And this is, remember, for instantaneous closure. For instantaneous closure, when your time of closure is 0. This is the time of closure, Tc, this is 0. Although it is physically impossible, because when we close the valve, it takes some finite time, 0.1 second, 0.2 second, 1 second, 2 second. But this case help us to understand the real cases that we are going to discuss now. Before we do that, this up and down which you saw here, you see this one here, and then this negative pressure, this you can see physically. You can see here that the water is suddenly closed. You can see here the positive and the negative. This is how the pressure wave travels. You can see suddenly close the valve, see the pressure goes up and down until equilibrium is reached. This is for real cases. No pressure change here. When you suddenly close, you can see the pressure wave, it travels back and forth. This is water hammer pressure. You can see here the pressure variation for real cases. So if we want to avoid this we are going to study how to reduce the water hammer pressure to keep it within the limits so that the pipe does not burst or damage. You can see the effect that moves. Same can occur in our blood flow in the veins also. This is due to the action of the heart that these waves can generate. So you already saw this variation of pressure that is resulted due to this phenomena known as the water hammer. We studied to calculate the pressure increase due to this water hammer. Now, before we discuss the two real cases, there is one thing which I want to explain, is that earlier you saw that when the pressure wave is traveling here, if I come back to here, this velocity is 0. This velocity is 0. Let's say from here to here, what is the velocity? 0. So when the velocity is 0, then in that case, what will happen is that for this situation, this diagram which I show you here, this CR, which is the situation here which is shown for the due to the head loss. When the pressure wave, it travels from N to B, the water in Bn here, what is V? V is equal to 0. V is equal to 0. And for zero flow, the hydraulic grade line CR should be horizontal. It means that this should be horizontal because we have zero flow. So that's why this should be CS. There is a tendency it should flatten out. Instead of CR, it should be horizontal, because if velocity is 0, so this is due to what? This is inclined due to the friction. So the head loss is a function of the velocity. So if V is 0, it should be a horizontal line. So thus there is a tendency for the grade line to flatten out for the portion Bn. For this portion Bn, it can flatten out. Clear? So hence, instead of transient gradient having the slope imposed by the friction, this CR, having this slope imposed by the friction, it will approach the horizontal line CS. It will approach the horizontal line CS. So as the pressure at C cannot change, clear? Thus the pressure head at N will be raised to a slightly higher value than NR, slightly higher than NR shortly after the valve is closed. Clear? So this increase in, it is written in your book that this increase in pressure here, this is also verified by tests. The tests that we have conducted on water hammer. So this is also borne out by the tests. Clear? So because of this effect, and if we consider the damping, so the damping is the decrease in amplitude of the wave. This is for the real case. So that's why instead of horizontal, it is shown as sloping up. That's why you see that, clear, when you consider the pipe friction as well as damping. So you see that instead of horizontal, which I show you earlier, the horizontal here, this was horizontal here, you see, this is horizontal here. So if we consider the damping, because here you see damping neglected. So if we consider now the fluid friction and damping, so then in that case, what will happen is that it is sloping up, and similarly on the other side sloping down. This is when you consider pipe friction and damping. And damping, what is this? Is the amplitude, clear, of this pressure wave. So you see that what we see, because of this, there is increase in pressure, and then with the help of time, if I correctly draw it, it decreases. This is the amplitude. It decreases with time, the effect. So you can see here, it reduces. Clear? It reduces. So it means that, let's say, this is now the effect here due to the damping, then here, then small, then small, then small, and eventually this effect is here. This is how the effect will occur due to this water hammer. But this initial increase in pressure, that is damaging. It can burst the pipe, it can damage the pipe, it can cause leakage to the pipe. But this we have to avoid in order to protect the systems against the water hammer. Clear? So that is important, and we are interested to calculate. So these waves will be decreasing amplitude until the final equilibrium pressure is reached. Okay. Now we consider the real cases. Clear? So we consider the rapid closure. So in the rapid closure, the time of closure is greater than 0. but it is less than TR, the round trip of the pressure wave. So this is called the rapid closure. In this case, previously what was Tc? Equal to 0, but in here 0 is less than Tc and it is less than Tr, the round trip of the pressure wave. This is now the situation. So it means that now we close the valve in certain finite time which is greater than 0, but less than this round trip. So this is known as rapid closure. Clear? This is known as rapid closure. Now in this case, this is the diagram which is shown for the rapid closure for actual experiment. This is actual data. These are actual measurements of pressure changes at the valve, point N that we just saw at the valve. So you can see that's why the values are written here, plus 150, minus 150, and this is the time in seconds. And this is the increase in pressure due to water hammer. So this is now for the real case. Now in this case, what is happening is that this time, the round trip, it takes is same 2L by Cj. At earlier we saw that you have a pipe, and at the end of a pipe we have a valve, and this total length is L from here to here. So this coming from valve to the reservoir and then coming back here, this round trip at the valve, this is the valve. This is given by this equation earlier we discussed, S is equal to Vt 2 times because round trip. So when we have rapid closure, the increase in pressure will be how much? Because in instantaneous we already developed the equation. So remember, the maximum pressure is the same as for instantaneous closure. So if we have a rapid closure case, in that case what will be the maximum increase in pressure? That will be the same as the instantaneous closure. So you can use the previous formula to calculate the change in pressure. Clear? You can calculate the change in pressure. So the duration of the maximum pressure is Tr minus Tc, because previously it was Tr. Now we have Tc which is not equal to 0, so the duration is this. You can see here the duration for which the maximum pressure will remain at the valve. What was that? 2L by Cj. If I go back and show you the diagram here, what was the duration for instantaneous closure? 2L by Cj at the valve. The pressure for how much time will remain at the high value? 2L by Cj. For this value, the increase in pressure will remain. Clear? Now, for case of rapid closure, what is the situation? That the duration is Tr minus Tc. So what is happening is that if I go back and show you in this diagram here, for rapid closure, you see that from here up to this point here, the increase in pressure, that is the same up to here as for instantaneous closure. So now we discussed that the increase in pressure for rapid closure is the same as the instantaneous closure. But in case of instantaneous closure, the increase in pressure will not travel all the way to the reservoir. You see here, for rapid closure, we do not have here. Up to this point here, X naught. Why it is not possible to extend all the way to the reservoir? Because what is the situation here, that at X naught, TR is equal to TC, the time of closure. There is some distance X naught that we can calculate. You already know Cj, you already know time of closure here, you already know it is some finite time of closure, not zero. We can calculate this Xj. And this X naught for Cj and Tc by 2, this X naught is such that for this, the round trip is equal to the time of closure. Clear? For this X naught, the return time is equal to the time of closure. So if I go back in here, this X naught, you see, when the point is here, it will go up, and the maximum pressure will occur for this point for flow in this pipe here. For this X naught here, it can still occur here and go to the maximum point as the wave is traveling here. But for this point here, as it moves to reach the maximum pressure, as this point moves to reach the maximum point here, as this point, this pressure is here, as it tries to reach to this point here, it cannot reach. Why? Because the pressure loading wave which increases here, it has returned back, and it will keep this up to this value here. It will not allow this to move to this point here. You understand what we mean by this? Because you take some time to close the valve, not zero, as was case in instantaneous closure. So that's why when this point, any pressure here, it will try to reach here, and when it comes back down here, when the unloading pressure wave reaches here, it brings this pressure down. So the idea here is that for this X naught, time of closure is the same as the return trip. So that's why when this point here, it will try to go up. Before it reaches the maximum value, it is caught by the return unloading pressure wave. The unloading pressure wave already arrived here, and it will keep the pressure here. It will not allow the pressure to reach to the maximum value. So it means that the more you move closer to point M, so the lesser the pressure will be as compared to the maximum value. And this uniform decrease, this is assumed to be uniformly decreasing at the pipe inlet. The thing is that for this distance, if any point X is less than X naught, the maximum pressure is never achieved in case of rapid closure. This is the conclusion. Why? Because the pressure is trying to increase to the maximum value, but the unloading pressure wave has reached there. It will not allow it to reach to the maximum value. This is because now your time of closure is not equal to 0. We have rapid closure. This is not equal to 0. If it is equal to 0, you can see that all the points will reach to the maximum point on this transient hydraulic grade line. But since now we have rapid closure, Tc is not equal to 0, it means that for all the points on the pipe, it is not possible to experience the maximum change in pressure. All the points that are on a pipe greater than this x naught, here all the points on the pipe, they will experience this pressure delta P by gamma, the maximum pressure due to water hammer. But all the points here less than x naught, they will increase a pressure less than delta P by gamma. What is the reason? That the moment it tried to reach to the maximum value, the unloading pressure wave has returned and not allow it to reach to the maximum value. This is the reason. So it means that in case of rapid closure, all the points on the pipe cannot experience the increase in pressure. Only those points for which x is greater than x naught, they will experience the maximum pressure. But x less than x naught, the pressure will be less than the maximum pressure. Clear? And this x naught we can calculate. This we can calculate using this formula. And for this x naught, the return time is equal to the closure time. That's why the maximum pressure cannot occur for any point less than x naught. Now another difference between this rapid closure and the instantaneous closure is the sloping line. You see here the sloping line. What was the line in the previous case? Or let's see here, vertical line. Instantly the pressure increases. See here, instantly the pressure increases. But in this case, you see here the sloping line. And it should be this sloping line, it should be this sloping line, or it should be this sloping line. This will depend on nature of the valve operation. How you open the valve, this nature of the sloping line will depend on that opening of the valve operation. And you can see the maximum pressure duration is less than that as compared to the instantaneous closure, which is given by TR minus TC. Now you can watch this video. Here I already show you here, this you can see here the variation, but in here you can see this. You see, when you close the valve, you suddenly close the valve. See here, this is for the real case. This is what you observe here. When we close the valve, instantaneously what you observe? You observe like this. And then due to damping effect, the equilibrium is reached. This is what you saw in the video. Actual cases. Clear? Next we have the slow closure. When we close the valve very slowly. So in that case, the time of closure is greater than the return trip. So now what it means? if the time of closure is greater than the return trip. It means that the maximum pressure in case of instantaneous closure, rapid closure, that is never achieved. When we very slowly close the valve, the pressure increase will occur, but it will be very small. So this is a better condition, clear? Because the time of closure is now greater than return trip. So that's why you can see that previously the increase in pressure is above 150 for actual case, because rapidly we close the valve, but the return time, it is less than the return trip. So that's why the maximum pressure is reached. In this case, now the time of closure is more than the return time of the pressure wave. So that's why the moment it tried to go to the maximum pressure, this is the maximum pressure change, delta P by gamma. The moment any point it tried to reach here, the pressure wave travels and then it comes back here. So it will not allow the pressure to occur, but it will keep the pressure lower. Let's say up to here. This happened, and you saw in the rapid closure also for X naught. For X naught. Because the point is trying to reach to the maximum value. Clear? But what is happening is that the return trip of the pressure wave is small. The time of closure is large. We still close it. It's not completely closed. When it completely closed, it will reach to the maximum. This is what we saw. But we still are closing the valve, so the pressure is increasing. The pressure will increase and it will reach the maximum value for the given conditions of the pipe and the fluid. But because now the time of closure is more, this pressure try to increase, reach here. But as it try to increase, the pressure wave travels, and then the unloading pressure wave comes, and it will not allow the pressure to reach here, but it will keep the pressure up to here. This is what happens in this case also. For X naught and less than X naught, you see, the greater pressure is not achieved, the maximum. So in case of slow, you see for rapid closure 150 pressure head, but for slow it is 60. Why? Because the unloading pressure wave has already come back. We are still closing the valve, and that's why it will not allow the maximum pressure to occur, but keep it lower than that. This is the slow closure. So it means it is desirable. This is what we want, to keep the pressure low. So that's why here you can see that the time of closure, it is more than the return time for the pressure wave. So in this case, the maximum pressure rise will be less than the rapid valve closure, because the wave of pressure unloading will reach the valve before the valve is completely closed. This will prevent any further increase in pressure. You see, you close the valve in 3 seconds, but the unloading pressure wave has come back in 1.4 seconds. So that's why it will not allow the maximum pressure to reach. It will keep the pressure less. So that's why the equation for delta P by gamma that we developed for instantaneous closure and rapid closure cannot apply here. So the maximum pressure now we say delta P dash developed by slow valve closure is given by what we say. We say that in this case now the X naught is greater than L, because we still close the valve and the return trip is less. So that's why we can assume x naught is greater than L, the entire length of the pipe. So in x naught, what is the pressure? This is the pressure that we draw for x naught here. This is the pressure that we draw for x naught. So now coming back here, you see this is what we saw, uniformly decreasing pressure. So now we are interested to calculate this delta P dash. Delta P we can calculate. X naught we can calculate. L is given. We can calculate delta P dash approximately by this relationship, similar triangles. Delta P dash by delta P is equal to L by X naught. So now we already know L, X naught and delta P from previously. So you can calculate delta P dash from these equations. This is the increase in or change in pressure due to slow closure, and it will be less than the rapid or instantaneous closure. Okay. So in case of rapid closure, the increase in pressure that we can calculate same as for instantaneous closure. But in case of slow closure, then this formula we can use to calculate the increase in pressure. Now next we have protection from water hammer. Now we saw that what is water hammer phenomena. We saw the physics of the pressure waves that travel back and forth and cause this increase or change in pressure. Then we studied instantaneous closure, where the time of closure is 0. It is ideal case, but it helps us to understand the real cases. So we calculated the change in pressure formula, the pressure that can occur due to water hammer. Instantaneous closure same as rapid closure. In case of slow closure, then we can use this formula to calculate the maximum pressure developed by slow valve closure. Now, as I said that this water hammer, it is undesirable. How we can protect against this water hammer? Because water hammer can damage the pipes, it can burst the pipes. So a pipeline may be protected from damage by water hammer by connecting to it any variety of devices that keep the transient pressures within desired limits. These are given in your textbook. For example, we have slow closing valves may be used to control the flow, and bypass valves can divert sudden changes in the flow. Automatic relief valves may be connected to the line to allow water to escape when the pressure exceeds certain value, and similarly air valves may be fitted to admit air into the line if the pressure falls too low. Air chambers include so-called bladder accumulators and hydropneumatic surge arresters. They contain air or gas which acts as cushion to absorb the pressure changes. Pump flywheels have been used to absorb energy by increasing the inertia of the rotating element, and they thus increase the time required for incremental changes in the flow rate. Surge tanks are standpipes connected to the pipeline that store liquid when pressures are very high and return it to the line when pressures fall. Some surge tanks admit liquid through an orifice, which in addition helps to dissipate energy. Differential surge tanks have multiple chambers with interconnections. The different water levels that occur in the various chambers help to dampen out the oscillations. So you can see that these are the devices that we provide to have protection against the water hammer. So you can see that in case of the hydropower plants where the water is supplied through a tunnel, which is known as a penstock. So if we have to stop the supply of water to the turbine, then the pressure will increase and it can burst the pipe. So that's why these surge tanks are provided. These surge tanks are provided so that the water rises in this pipe here momentarily and it can avoid the increase in pressure. So the pipe is protected from the water hammer pressures. Clear? You can see here that in hydroelectric power plant in a dam in Iraq, you can see that here 4 accumulators which are similar to surge tanks, they are provided. So whenever we want to stop the water, then the water will rise in these tanks and the pressure increase that can be avoided in the piping system. Clear? Because due to the rapid closure of the gates, it will increase the pressure and it can damage or burst the pipes. So these accumulators, these are provided protect against the pressure transients. Similarly, you can see this is another dam in the US. So you can see that the surge tank is provided here. This is a vertical surge tank open to the atmosphere. And what will happen is that you can see huge quantity of water is stored behind this dam, and you can see the powerhouse here. So if we need to protect the pipes, so the water will rise in this surge tank, and that is how the water hammer pressures, they are reduced in the pipe system and they are protected against the water hammer pressures. Clear? You can see here that this is their tank, and if the pressure increases, then the water can rise in the tank.
Wow.
So this is what you can see here, that in the tank, this water will rise and it can protect the pipes from damaging or bursting due to water hammer pressures. In the water supply systems, now we are providing these known as the water hammer arresters. In the Western countries, in the water supply systems, they provide this protection from water hammer. This is known as the water hammer arresters. So what will happen? The water will rise due to the high pressure and it will push this spring against the air, and this is how it will absorb that water momentum, and the pipes that will be protected against the high pressures, otherwise the pipes will be damaged. You can see here, when you suddenly close the valve, these pressure waves will generate, and because of this water hammer arresters, then what can happen, that it can absorb, clear, these high pressures, and you see that the pipe can be protected against the water hammer pressure. So these are manufactured by different companies, come in a variety of sizes. So these are in water supply system. We use such type of devices to keep the pipes safe. I will show you just one video here. This is a company which made this video. So in water supply systems, you can see here, due to the water hammer, suddenly close the valve. You can see here the effect of water hammer. It can create noise and vibration in the pipes. You see the noise and vibration it can create, and it can cause leakage in the water pipes joints. So that's why it is very dangerous. So what we can do is that we can provide this water hammer arresters. You can see here in this case. So when the water is shut off, so then in that case it can help prevent the water hammer pressures. You can see here it will fill the air chamber. So it can provide protection in the water supply systems. If you are interested, there is one paper available, Hydraulic Transient Analysis of Surge Tanks, a case study of Satpara and Golan Gol hydropower projects in Pakistan. This is published from UET Lahore. This is available online. You can study this paper there. They discuss in detail the hydraulic transient analysis of the surge tanks, which we provide for protection against the water hammer. Clear? This is the surge tank. This figure is in that paper. So when you supply the water and you need to suddenly stop the water, this is huge quantity of water coming from the dam. We provide these surge tanks, and they provide protection against the water hammer. You can see here. So that's why we need to design these surge tanks in order to withstand, for any given condition, the increase in pressure, and we can protect these pipes from damaging or bursting due to the water hammer phenomena. Now let us solve one or two problems to finish this. We have this 250 millimeter diameter pipe, flush entrance, friction factor is given 0.026. The pipe length is 1000 meter long. It delivers water from a higher reservoir to a lower reservoir here. The difference between is 75 meter, this delta Z, which is given 75 meter. After a valve near the downstream end is suddenly opened. Now when we suddenly open this valve, what will be the steady flow velocity in this pipe? What will be the steady flow velocity? We already discussed in the previous lecture, develop an equation for steady flow velocity. And how long after the valve is opened will the flow velocity be 1/3 and 2/3 of the steady velocity? We already discussed this topic, the last topic in the previous lecture, where we study approach. The topic was approach to steady flow. So we develop equations there that you can use. Now L by D is 4000. So it is greater than 1000. We can neglect the minor losses. This is the K that we discussed previously. So now in this case, this is 0 and this is 0. Clear? Because we neglect the minor losses, we have submerged discharge. This will include this submerged discharge coefficient. So that's why we only have FL by D. So this is given, we can calculate K. Everything is given, just plug in the value, we can calculate K. And this is the formula that we developed in the last lecture for steady flow velocity. 2gh by K. What is H? H is your delta Z now in this case. So you put the values and 3.76 meter per second. This is the steady state velocity. Now it is asked that what is the time that we will approach Vs, the steady state velocity? How much time? This we developed in the last lecture. 1/3. 1/3 of this. How much time it will take that the velocity will approach the steady state velocity? And 2/3 of the steady state velocity. So for V is equal to 1/3 of the steady state, the time is, you just put values in this equation here, 1.772 seconds. And for 2/3 of the steady state velocity, when v approaches 2/3 of the steady state velocity, the time taken is 4.11 seconds. So this we discussed in the previous lecture. Now next we have water flows at 10 foot per second in 400 feet long steel pipe of 8-inch diameter with 0.2 inch thick walls. Calculate the pulse interval TR, return trip, and the maximum pressure rise theoretically caused by instantaneous closing the end valve. Now instantaneous closing the end valve. So we calculate Cj, the joint celerity of pressure wave. C is given, EV and E are given. So we can easily put the values. This is now Cj, celerity of pressure waves, joint or combined. When J is written means the combined, because here we treat the pipe and the fluid both as elastic. The return trip, round trip of the pressure wave, we already discussed. It is given by 2L by Cj. So you put the values. Now in A, when you completely close the valve, what is the maximum pressure rise? So when you completely close the valve, this is the formula. We just discussed and derived this earlier. Delta P is equal to rho Cj into V. So just put the values. This is the increase in pressure, and this is in pressure head in terms of feet of water. In the second case with partial closure, Cj and Tr remain the same, partial closure. But now we have V2 because it is not complete closure. When it is complete closure, this is 0, and this was the formula in part A. But now we are still closing, it's not. So that's why the velocity is not reduced to 0, to V2. So then in that case, it is given 6 foot per second, partially reducing the velocity to 6 foot per second. It is given. So just you put the value, and now in this case, the pressure is this much. Now see what was the pressure in part A? 79,000. And now in here, what is the pressure? Around 32,000 pounds per square foot. So that's why slow closing the valve, it will keep the pressure less. This is what we studied earlier. This is a problem from 8th edition of the textbook. The elasticity and dimensions of the pipe are such that the celerity of the pressure wave is this. Now Cj is given. Suppose the pipe has length of 600 meter. This is 600 meter length pipe, and the diameter of 1.2 meter. The flow rate is initially 0.9 cubic meter per second. The discharge water is flowing. Find A, water hammer pressure for instantaneous valve closure. So now we need to calculate for instantaneously time Tc equal to 0, what is the pressure. So we calculate the velocity, discharge is given, velocity is 0.796, and now for instantaneous valve closure, delta P is rho Cj into V. This is what we discussed. So just you put the values, this is the pressure, 764 kilonewton per square meter. When you suddenly close the valve in time Tc equal to 0, then this will be the increase in pressure, the water hammer pressure. Clear? Part B is approximate pressure at valve. This is the valve. If it is closed in 4 seconds. Now the valve is closed in 4 seconds. How much increase in pressure will occur? So now it is not instantaneous closure, because for instantaneous closure, now here Tc is what? This 4 second is your Tc. Now it says that when Tc is 4 seconds, so what will be the increase in pressure? So we need to first calculate that it is slow closure or rapid closure. So we need to calculate the round trip of the pressure wave. So it is how much? 1.25 seconds. And you close the valve in 4 seconds. So it means it is less than the time of closure. So it means it is slow closure. So for slow closure, we develop this equation. Delta P dash is equal to 2L by Cj divided by T is equal to delta P. So now we already know delta P from here. You can plug in the values, and now for slow closure, it is 238.75 kPa, kilonewton per square meter, kilopascal. So you can see 764, and then with slow closure, the pressure is 238.75. That's why we would like to slowly close the valve to keep the water hammer pressure reduced. Part C is, what is part C? The water hammer pressure at valve, if it is manipulated so that the flow rate drops from 0.9 to 0.3. Now the flow rate drops from 0.9 to 0.3. The discharge is reduced. So what is the water hammer pressure? So now for case of the partial closure, because the flow is reduced to 0.3, now the V2 is 0.262 meter for 0.3. 0.9 to 0.3 we reduce, clear? So now instead of rho C J into V, we have V2 because it is partial closure. If it is complete closure, V2 will be 0. So now you can plug in the values and you can calculate the water hammer pressure. And for D, maximum water hammer pressure at point in the pipe 90 meter from the reservoir, if a 1 second valve closure reduces the flow rate from 0.3 to 0. So now you close the valve in 1 second. What is that? What is the time of return trip? 1.25. And now you close the valve in 1 second. So what is that? Rapid closure. Clear? So for rapid closure, we first calculate X naught. TC is now 1 second. Cj is given, we can calculate X naught. So it means that any point less than X naught will experience a pressure less than the maximum pressure. But any point greater than X naught will experience the maximum pressure. This is what we saw. This is what we say. Clear? So in this case, what I want to say is that up to this X naught for 80 meter, all the points will experience the maximum pressure. But any point less than that will experience a pressure less than the maximum. Why? Because the unloading pressure wave has returned and it will not allow the pressure to reach to the maximum value. This pressure which is here, it cannot reach to this maximum value. Why? Because the unloading pressure wave has returned and it keeps it to lesser than the maximum value. This is what we studied earlier. So now it is asked to calculate the pressure at what? 90 meter. So 90 meter is less than 480 meter. That's why this pressure will not be occur at 90 meter, less than that. So that's why for that we calculate the velocity for 0.3, and now we calculate the pressure delta P, that is equal to 254, because the maximum water pressure hammer at the point in the pipe 90 meter reduces now the flow rate from 0.3 to 0. So that's why for 0.3 now, the maximum pressure that can occur is this. So now we can compare, this is now known 90 for 80 delta P, we can calculate from similar triangles. So at 0.90 meter, delta P will be equal to similar triangles, 254 divided by 480 equal to delta P by 90. So 90 comes here, 47.7 kilopascal, kilonewton per square meter. This will be the pressure that will develop at 90 meter from here due to the water hammer. but it will not reach to 254. Why? Because it tried to reach to 254, but the unloading pressure wave has reached, and it will keep it to 47.7 kilonewton per square meter.